In this video, we're going to talk about the controlling factors of the symmetrical components method. You're going to be able to visually see how symmetrical components can break down unbalanced phasors. And I'm drawing here the very common balanced Y source leading into the balanced phasor conditions that demonstrates simple voltage in this particular system. And if you notice, V1 equals V2 and it equals V3. Voltage is all the same. You don't have to concern yourself with complicated follow-up questions regarding subscripts. Are we talking about the voltage on phase 1, phase 2, or is it the voltage between 1 and 3, or anything like that? That is extra complicated. So in balanced situations like this, we just need to worry about voltage. Very simple. Or if we were talking about current, the same would apply. Now in unbalanced situations, this is no longer the case. You start to have to concern yourself with, are you talking about the voltage or current in phase 1 or phase 2? Is it the voltage between phase 1 and 3? Or how do we have to consider the individual voltage in a given unbalanced phase? And so instead of just talking about P equals VI and the V and the I being one thing, we've now escalated it to being 6 different things. Is it the voltage for one of 3 phases? Is it the current for one of 3 phases? Which of those are we talking about? How are those relating to one another, and so forth? So it goes from a relatively, in this instance, power calculation that is simple to a very difficult power calculation in the end once we encounter unbalanced conditions. And so what symmetrical components is going to attempt to do is break this down in a simpler way to get them to work together and not have to concern ourselves with all of these confusing distinctions we have to make. So now let's look at an actual unbalanced phasor set and see how we can work with them. So here we've got some graphics demonstrating separated phasors. We have obviously different phase angles and different phase magnitudes for A, B, and C. And then they can be shown together on the right-hand side in what is the common visualization of phasors having a shared point of nexus. And we see that they are demonstrated in this instance in a clockwise manner and asymmetrical. So these could represent voltage, these could represent current, these could represent any number of factors that we are concerned with in analyzing a circuit. But one thing you need to understand is they're not balanced. So we can't just say, for instance, if these represented voltage, that the voltage for this is one thing. We have 3 different voltages based upon the phases. So then what do? We need to get them broken down into component parts, and by them I mean these phasors need to be broken down into component phasors that do correspond to one another, that have some sort of commonality that allow them to interact with one another. And symmetrical components requires these to be broken into 3 parts. So what they're going to be is 3 essentially phase sequences. So for the A phasor, we're going to have 3 phasors to make up 1. For the B phasors, 3, and for the C phase, 3. And they are going to be represented then in positive, negative, and 0 sequence. These phase sequences can be demonstrated here below as I scroll down. So here are the symmetrical component vectors. Now what we're talking about is these are the component vectors that make up each of the individual phasors. So we see an A positive here, an A negative, and an A zero. What we mean by that is these are the 3 phasors that are the components for the unbalanced A phasor, and they are represented in their various phase sequences. So that A phasor breaks down into these 3 A phasors. This is from the A in the positive sequence, this is the A in the negative sequence, and this is the A in the 0 sequence. Now we don't arrive at these various 3 phases just by trial and error or by some magical, mystical process. There's actually some math that goes into it, and we're going to get into the math a little bit later. Let's talk about the controlling factors of how we arrive at these 3 phases. We talked before in our previous video about symmetry. So we see in the positive A phasor and the whole positive phase sequence that they are in symmetrical relation to one another, meaning all phasors share the same magnitude, and they also share a symmetrical phase angle difference. And what I mean by that is they're all 120 degrees separated from one another. Now these are controlling factors, and what I mean by that is this. You cannot have a positive sequence that has any of the phasors more or less than 120 degrees. And you cannot have a positive phasor in this sequence be greater or less than in magnitude to the other two. And the same is the case with the negative sequence. We see that we have symmetry being a controlling factor, both in phase shift and in phase magnitude. Now, as we go over to the zero sequence, we see no rotation. This is why this method is not called maybe something like matching components or exact corresponding components or what have you. We have another sort of example of symmetry being displayed in the zero sequence. And what I mean by that is this. They share the same magnitude and they have no rotation one to the other. So it's a sort of symmetry. It's a different symmetry than the other two phase sequences had, but there is still some symmetrical concept in play. So we need to break down one phasor into these three component phasors as we've discussed. And you don't do that, like we've said, in some magical way. There's matrix math in play behind all of this. And the matrix math is meant to correspond to these particular controlling elements. Phase angle, magnitude, and that there are three distinct phasors for one unbalanced phase in the above unbalanced system. So what do we do with these phasors in these particular phase sequences once we've got them to this point? Well, we can put them together in the standard head-to-tail vector addition and see what occurs here. We've got the A phasor from the positive sequence, the A phasor from the negative sequence, and the A phasor from the zero sequence. And you can see scrolled up here. So we've not done anything, but we've pulled these sequences apart and used the A's together, the B's together, and the C's together in head-to-tail fashion here. As labeled at the bottom, A goes together, B goes together, C goes together. Now, it's fascinating. What we see is we see what we can start to anticipate as differing resultant vectors from these being added together. Now, it's fascinating because we've got what seems to be matching symmetrical phasors when they are in their positive, negative, and zero sequence. But once we've broken them up and then added them together, we get different resultant phasors. So what we've done, in a sense, a good way that you might want to think about this is it's like we've got three different fractions and we've found kind of a common denominator, if you will. And it's not absolutely, it's just kind of a way that you can think about it. We've got these common denominators that allow us now to add the positive sequences together, the negative sequences, and the zero sequences together in a concise and understandable way. But in the end, once they come together, they still form unbalanced phasors. So we have balanced phasors in these sequences shown, but in the end they equal out to the resultant phasor, which is unbalanced. And we're going to show that right here. As we scroll down, we're going to see the original phasors with the symmetrical component vectors shown next to them. So the black arrow here is the original unbalanced for the three, and we see how they can all add together. It's pretty fascinating and interesting, really, when you look at that, how symmetrical, how common the component phasors are, and yet how uncommon and asymmetrical the resultant phasors are in this case. Now, you can also see, if you start to use sort of mathematical intuition, that when we work on the algebra upcoming, the matrix math that's going to come, we see that our controlling factors of 120-degree phase angle distribution between the positive and negative sequence, the required matching of magnitudes, the zero phase difference between the zero sequence, and so forth, are going to create sort of variables. So you can't just change one A phasor of the positive and not change the B phasor of the positive, and so forth. So these are all variables that are contingent upon one another, and like we've said, are contingent upon the controlling ideas of symmetry and three-part components for one phasor in an unbalanced system. So scrolling down now, we can move back to the original phasors and see exactly where we started out from. We've got these three phasors represented by the component phasors above. So there's the A phase there shown, and we can keep drawing our lines from the other sequences and the other phasors to correspond all together. Not too hard, actually, when visually represented like that, to see how this all works. And in the next video, we're going to show the math behind all of this.